Hey class, welcome to our 5.1 video on work. Now, when we were in class, we kind of did a little bit of an example to try and figure out how we know when we actually do work on something. So if you're watching this video, I want you to do something. I want you to take your pencil, and I want you to put it on your desk, and I want you to push it off of your desk. I know it might seem a little weird right now, but go ahead and do that. Then I want you to get up and I want you to find the nearest wall. I want you to find whether that's in your house or in your classroom. And I want you to try and push as hard as you can. Like get a little bit out of breath, like you're pushing really, really, really hard. I want you to think, which one do you feel like you did more work? Well, in reality, you probably feel like you did more work pushing the wall because you put a lot of effort into it, and we equate the word work to effort. However, in this example, you actually did more work pushing your pencil. And here's why. So when we talk about work, our definition for work is the force applied to an object over a distance. So even though you pushed with way, way, way more force on your pencil, you did not move it at all. So technically you did no work. So you could be holding the boulder in place for 3 hours, saving people from it collapsing on them, and you technically, in physics terms, did no work. So when we think about work, we have to think about how far I'm pushing something. So you actually get an equation that looks like this. So you have work is equal to the force on an object times the distance the object moves times the cosine of the angle between the force and distance. And we'll talk a little bit more about what that means later, but you end up with this. W is F times D times cosine theta, where theta, again, is the angle between force and distance. So we're going to jump into an example. This example should also kind of wake our brains up to some stuff we did in the past units about finding a free body diagram and looking at forces, and then again looking forward towards work in this situation. So let's go ahead and dig into our example here. We're going to have a box of some kind. We're going to have this box weigh 20 kilograms. That's going to be the mass of it. And it's going to be pushed along a flat surface. So we're going to do a force to the right. This is going to be F push. So FP is going to be 100 newtons to the right. We're going to have a frictional force, or FF, of 40 newtons to the left. Its weight, which is the force of gravity we know as mg, so this is going to be 200 newtons down. And because I'm on a flat surface, the normal force and the force of gravity are going to be equal to each other, also at 200 newtons. And my end game here, my goal, is to find the total work done on the object. And in order to do that, I have to find the work done by each force. So the sum of all of our works, so to find the total, that's going to be sum of our works, is going to equal the work done by the pushing force, plus the work done by gravity, plus the work done by friction, plus the work done by the normal force. You might be asking, well, how can I figure that out without knowing a distance? Well, that is a requirement, so we're going to draw here that we push this object 10 meters. So I have a bunch of forces, I have a distance, and we're going to figure out what that cosine theta means. But let's start, we're going to work in order here. So let's find the work done by the pushing force. Well, I'm going to pull in my work equation, which was the force, so force of my push, times the distance the object moves, times cosine theta. Well, the pushing force was 100 newtons, times the distance of 10, times the cosine of what is my angle. Well, you can use your fingers to help you figure this out. And if we think about, take your one of your hands, and you're going to point in the direction of the push, which in this case is to the right. So there's my force. And what direction is it going? Well, it's also going to the right. That's my distance. So that means the angle between these two, going the same way, is going to be 0. And as a quick side note, we're going to make a cosine theta cheat sheet here. And just some quick ones to know. Cosine of 0 is equal to 1. Cosine of 90 degrees is 0. And the cosine of 180 degrees is equal to -1. So it's going to come in handy here. Because cosine of 0 is 1, so I have 100 times 10 times 1, which gets me a whopping 1,000 somethings. And we measure work in something called joules. So I have 1,000 joules of work done here by the pushing force. Now let's figure out the other one. So we're going to do the work now done by gravity. So it's going to be Fg times distance times cosine theta. So it's going to be, gravity is 200 times my distance of 10 times the cosine of something. So let's do what we did earlier. The force of gravity points down. The distance points here, and that forms a 90-degree angle. And the cosine of 90 is 0. So I'm going to have 200 times 10 times 0, which means it does 0 joules of work. And you might think, well, that's kind of weird, but it's a big force, and we're moving. But the thing is, it's not pushing any in the direction that we're actually moving. It's entirely in a different plane. So think about, kinematics, forces. We like things to be in X and Y. We like them to be matched up. So that's why it's not matched up here. So 0 joules. All right, let's look at the work done by friction. It's going to be the force of friction times distance times cosine theta. So it's going to be friction was 40, distance is 10, and then what's my cosine function going to be? Well, let's do what we did earlier. Let's look at it again. So I have the force of friction pointed to the left, and I have distance pointed this way. Here is going to be 180 degrees. And as we looked at earlier as our cheat sheet, cosine of 180 is -1. It's going to be 40 times 10 times -1, which gives you -400 joules, which tells me, yes, you can have a negative work. It's important to realize that. Lastly, let's look at the normal force. So work done by normal. That's going to be the normal force times distance times the cosine of the angle between those two. Be 200 times 10 times the cosine of what? If you're catching on, you can just figure out the problem there. But if we look, we've got force up, distance here, 90 degrees, and 90 degrees is 0. So this looks just like gravity. 0 joules. Now what was our goal? Our goal here was to find the total work. So that means I got to take these numbers and I got to plug them in up here. So it's going to give me 1,000 plus 0 plus -400 plus 0, which gives me a whopping 600 joules of total energy. Now, as you look towards our worksheet, it's just going to be applying the equation in different ways. And make sure you're using our guess method to solve. So notice I had my picture that had all of my stuff in it, but you want to make sure that you are identifying variables and solving using the equation, rearranging to solve maybe for distance or for work or for force. You're kind of rearranging it around to figure out. So as you look forward towards that worksheet and you're working on it, make sure to come ask questions, email me, talk to me in class, but good luck, and don't forget to be awesome.